All right, so welcome back. What we're looking at now is finding the area that falls between two curves, and we must be very careful as far as how we set up integrals. So in this problem, we want to find the area that falls between r equals 3 cosine theta, that's this graph here, this black graph, and r equals 1 plus cosine theta, this cardioid. We're just looking for that area in the first quadrant. So if you notice between those two graphs, in the first quadrant we have this kind of moon shape, half moon shape piece, and then there's actually a little bit more area right here. But it's really important when we set up our integrals that we do set up our integrals to make sure that when we do an integral that these graphs are actually being graphed for those values. Otherwise, we have to do it kind of separately, and we would have to do like the area of the one piece, right? Work that out, do the area of the other piece, work that out, and then do their difference if they're not being graphed over the same theta values. So that's really important. It happens for these two in the first quadrant that everything does get graphed just like you would want. So let me just real quickly fix my a here for my step. Say a to 2 pi, step of pi over 12. So we can see that as I graph in the first quadrant here, these guys are graphing the normal thing. If you looked at the xy graphs of 1 plus cosine theta and 3 cosine theta, they are both positive in the first quadrant. So these two graphs come up, they do intersect, and then they continue to continue over to pi over 2. At that point, we're not worried about anything else. The rest of the graph, you can see the green graph actually gets reflected down into the negative range, finishes its graph at pi. The red graph is continuing, but again, none of these things matter because we're only interested in what's going on in the first quadrant. So these are graphing on the right values. We do notice they do intersect here. And so when we're graphing these, we're always asking the question, as I look radially from the origin out to the graphs, which one am I coming to first? Which one am I coming to last? And notice that that switches here. That actually switches here. That actually switches. Okay. So the green graph is the outer graph for a while until we reach this point here. And then the red graph takes over. Okay, until we finish at pi over 2. So we're looking at that question again as I come out. So we have this point of intersection, which I'll tell you what it is in a moment here. You could, of course, graph the XY graphs to find it directly. But we're looking here as we come out radially, which one am I coming to? Which one am I coming to first? And we can see that the black graph, the 3 cosine of theta is the one that I'm coming out to first, or second, and I'm crossing the red graph, the cardioid, 1 plus cosine of theta first. But then once I pass this point, which by the way happens at pi over 3, again, we could easily find that if we looked at the XY version of the graph. That's probably the easiest way to find that on Desmos. 1 plus cosine x and y equals 3, not cosecant. Try that again. 3 cosine x. And we can see they cross right there at pi over 3. Okay, so that's that first intersection point. And that's the only one that matters for us in this problem. Okay. So back to our function there. That intersection point happens at pi over 3. We're plenty of work to do, so we're perfectly fine in using a little bit of help here. And of course, later on, once it passes pi over 3, if you're drawing the radial line, you'll see coming into this area that would, again, we're crossing the black graph first, so it'll be the inner graph. So again, if you didn't do this, if these weren't graphed over the proper regions, like if this was being graphed from 0 to pi over 2, but this stuff here was being graphed from like pi over 2 to pi, we'd have to find those regions separately then, right, and then do the difference of their area. But since they are being graphed over the same theta values, we can actually do it as one big giant integral. Okay, and again, the process, remember, area in polar coordinates is again the integral of 1/2 of the function squared d theta, where again f is the radius. So setting this up here, our first piece, we're actually going to do two pieces. So we're going to have this first piece, which will be this area. Which we'll have to do. And we'll have to do this second piece, which is this little tiny sliver over here. Okay. So those are the two pieces that we're looking at. Okay. So let's focus on the blue piece. So setting up our formula, area would be 1/2, right? Integral 0 to pi over 3. And let me just fix that. That's not quite what I wanted. Make that look a little nicer. Try this again. Area to pi over 3. And then that would be my outer function, which is again the 3 cosine theta. So 3 cosine theta, quantity squared, minus the inner function for that part, which is my 1 plus cosine theta. Quantity squared d theta. Right? And then we set about working out this integral, which is going to take us a little bit of work. Okay, so with that in mind now, let's do some expanding here. 1/2 integral 0 to pi over 3. Now when I multiply this out, that'll be 9 cosine squared. But I'm subtracting off this piece, which is 1 plus cosine theta times 1 plus cosine theta. So when I multiply that piece out, I'm going to have a cosine squared. So I'm going to have a 3 cosine squared minus a cosine squared, which will leave me with an 8 cosine squared theta. And then when you multiply this out in the middle, you're going to have a plus 2 cosine theta. So that'll become minus 2 cosine theta. And we have a plus 1, which will now actually become a minus 1 d theta. Okay. And then some more simplifying that we need to do. Just a little bit more simplifying that we need to do. This 8 cosine squared theta, remember, would actually be 8 times 1/2 of 1 plus cosine 2 theta. Remember that identity, 1 plus cosine 2 theta over 2 is cosine squared. So that's actually going to be 4. So you're going to have 4 of that. So simplifying, now I'm going to have 1/2 the integral from 0 to pi over 3. And if I multiply that out, 8 times 1/2 times the cosine will give me 4 cosine 2 theta. I'm still going to have the minus 2 cosine theta. And now 8 times 1/2 is 4 times 1 will be 4, but it's minus 1. So it will be plus 3 d theta. Okay, and at this point, we're now ready to integrate. So remember, for the cosine 2 theta, we're going to need a 2 to kind of go along with it. So we take one of the 2's away from the 4. So I have my 2d theta. Right? Because cosine 2 theta is going to need a 2 to go with d theta. So we pull that off. And then the other 2 that's left over is going to disappear from the 1/2. So, and then we just integrate the cosine of 2 theta, which would be sine of 2 theta. So again, that 4 there, take half of that, you're left with the 2. That 2 is exactly what we need to carry that substitution through, and so we do that. Next one, the 1/2 and the 2 there are going to cancel out. We just have integral cosine. So that's going to be minus sine of theta. And then finally, 1/2 times 3 would be plus 3/2. Integral of d theta is just theta. Right? And this will be evaluated between our endpoints, 0 and pi over 3. Right? And then we just start to work this out between our endpoints, 0 and pi over 3. So if we plug pi over 3 in and double it, we're going to have 2 pi over 3. Reference angle will be pi over 3. We're in the second quadrant. Sine of pi over 3 is square root of 3 over 2. And since it's in the second quadrant, it's positive, so it stays the square root of 3 over 2. And that'll be minus sine of pi over 3. But sine of pi over 3 is just square root of 3 over 2. Okay. And then we would plug pi over 3 in and take 3/2 of that. Notice the 3's will cancel, and we're just left with plus pi over 2. Okay. And then we work out the other values, plug 0 into it. Sine of 0 is 0. Sorry, sine of twice 0 is 0. Sine of 0 is 0. 3/2 of 0 is 0. So in the end, that first region, that blue region that we had, has an area of pi over 2. Has an area of pi over 2. Okay. Now, we turn to the second piece. Now, we could go through all of this process again in the second piece, where we're going from the rest of the way, pi over 3, to where it ends over here at pi over 2, right, where we're stopping. Right? So we could do that piece and set up the whole problem. But the only difference is which function is the front, which function's the back. So if I was to go and label the stuff inside here as, say, F, big F, then I could think of my second problem here, the second area, as being the 1/2, the integral from pi over 3 to pi over 2 of minus F d theta. And so it would just be do all the work would still be the same, and it's just going to be a minus in front of all these things. That's going to be the only difference. Every one of these things will have a minus put in front of it, because it's the same problem. It's just written backwards. So to save a little bit of work, I'm going to do exactly that. Okay, so it's still 1/2 of that stuff. And all that stuff, that had a 1/2 in front too. So that's all fine. So it's just going to be this stuff with a negative sign in front of it. Negative sine of 2 theta plus sine of theta minus 3/2 theta. And that's going to be evaluated between pi over 3 and pi over 2. So we go ahead and we evaluate. Twice pi over 2 is pi. Okay, twice pi over 2 is pi. Sine of pi is 0. So the first term is 0. Sine of pi over 2 is 1. Plug in the 3 pi over 2 piece here. Plug in the 3/2 times pi over 2. Right, that'll give me plus not plus, I'm sorry. That'll be minus. And that'll be 3 pi over 4 for the first piece. And then we go to the second piece. Minus. And then we plug in pi over 3. Sine of 2 pi over 3 is square root of 3 over 2, but we have a minus sign in front. Minus square root of 3 over 2. And then sine of pi over 3 is square root of 3 over 2. And finally, minus 3/2 of pi over 3. Again, the 3's cancel and we have minus pi over 2. Okay, so simplifying, we have 1 minus 3 pi over 4 plus pi over 2. And so that would simplify to be 1 minus pi over 4. And again, that is my red area. And then finally, we just put these things together. Pi over 2 plus 1 minus pi over 4. By the way, 1 minus pi over 4 is a positive answer. So we are getting an area. It's just a relatively small answer. Dang it. Keeps disappearing. There we go. 0.21. It's a relatively small answer. And so we combine that with the pi over 2. So we have pi over 2 plus 1 minus pi over 4. And that would simplify to be 1 plus pi over 4. So kind of a cool final result there, that the area here in this graph that falls between these two things is 1 plus pi over 4. And of course, if you looked at the picture and had symmetry here, you'd have to actually have double that stuff if you dealt with the other part where you are dealing with area between the two. And I guess you could also include these pieces too, if you really wanted to look at all of the area that fell between the two of them. Then you'd be also looking at this little pit in here, and we'd have to work that out as well. But if you just looked in the first two quadrants, you'd actually have 2 plus pi over 2. You double that area, which is kind of cool. Place to stop there with this example.